Okay, thanks for coming. And here we have Joël Bédard from Environment Canada. And he's a visitor here actually in 2015. And same year, I think he got his PhD from University of Quebec. And since then, he working for Environment Canada and did a very good job in data simulation. So that's his topic. That's high resolution ensemble background error covariance for 4D ENVAR system. Here you go, Joe.
Thank you, Ming.
Thank you.
Hello, everyone. I'm not too much of a, how you say that, official guy, so feel free to interrupt during the presentation and make this thing dynamic. So, as Ming said, I've been a postdoc at Environment Canada with Mark Buhner for the last 2 years. I've been hired to work on high-resolution satellite data assimilation. But the fact is, there is no high-resolution data assimilation system yet. So my first 2 years of postdoc, I've been working to develop that system. And this is what I'm presenting today. It relates to the work I did here 2 years ago because I've been working on the assimilation of surface wind observation, and in my last paper in 2017, we discussed actually the propagation of the information in the system from assimilating surface wind observation, and we realized that the background error covariance matrix was a big limitation to the propagation of the information. So this works just stack on top of my previous work that I did during my PhD at UQAM and here after my PhD. So today we'll be talking about background error covariances. I hope you guys are familiar with data assimilation, or else feel free to ask questions. So before I start, I would like to draw a picture of what we have in terms of system, like prediction system at Environment Canada, operational. Actually, let's focus on the regional component, like the high-resolution deterministic prediction system, so the HRDPS. So right now, the HRDPS is going towards operation, and it is a simple downscaling of the continental system. So there is no data assimilation for this system, and this is what I've been developing. So basically, the continental data assimilation system is based on the 4D ENVAR that draws its flow-dependent background error covariance matrix from the global ensemble. So in the future, we want to go towards higher resolution background error covariances so that we can propagate the information from the observation in a more proper way. So we need to develop a higher resolution ensemble generation system. So I think this is what is written on the slide. Yeah. So everything good so far?
Yeah, actually, I think Canada has the 4D VAR, right?
We used to have 4D VAR. There was I'll repeat your question to make sure it's on the recording. So Ming was asking if Canada still have the 4D VAR. The answer is no. The last paper with 4D VAR is a paper I have with Mark Buhner that we just published about FSOI, and it was developing a method for forecast sensitivity to observation without the use of a TL and adjoint of the forecast model. So there was a political decision to stop developing the tangent linear and adjoint version of the model because it consumes a lot of human resources. And because the model evolves so fast, we always have to rederive these equations. And so we went from 4D VAR to 4D ENVAR. So we replaced the TL and adjoint of the model by ensemble temporal correlation to bring the information from the observation back and forth in time.
So I have a question about the regional implementations. Are they running continuously cycling, or are they doing some kind of...
It's a continuous cycle.
There's no partial cycling restarting from the global analysis periodically?
Up to today, it's actually a partial cycle, but the one we're pushing to operation right now, it's a full cycle.
Okay.
So it's now fully cycling with IAU, incremental analysis update, and yes, and we recycle the physics variables as well. So you start already with the clouds and stuff, because before with digital filter we could not recycle the physics variable.
And how often do you cycle the original one?
Every 6 hours. All our systems are recycled every 6 hours. We have planned for the high resolution regional system, which is 2.5 kilometer. We have planned to go towards rapid cycle. So, but I'm not sure if we're gonna, like, what's gonna be, we're still working on that. So I don't know if we're gonna stop at 3 hours, 2 hours, or 1 hour cycles. It has yet to be decided. So a little bit of motivation, because I think in my title that I mentioned ensemble generation methods for the generation of the background error covariances. But I just want to keep in mind that in our actual systems, we still benefit from including a climatological background error covariance term. So if you see on the left, these are the famous scorecards from the French people at Météo France, and I think even the UK Met Office used that. So if you have a red triangle on the left, it shows that when using the flow-dependent background error covariance, it is better than the static one in the ENVAR. So we see that, well, I think it's well known that flow-dependent background error covariance are better than 3D VAR. But if you look on the right-hand side, we realize that making a hybrid between the flow-dependent one and the static one is even better than the fully flow-dependent background error covariances. I think this is because we have to localize ensembles because of the sampling issues, so that for long correlation we don't have anything that is flow-dependent. We force them to zero because of sampling issues. So the static P matrix just catch up for it because it's pretty good for the large scale balance. So it brings me to my presentation overview. So I'll have a couple of slides on the climatological covariance because we are still using it. And I'll be focusing mainly on ensemble covariances, but just read the last line there. As we are improving the background error covariances from ensembles, we will be able to reduce the ratio of the climatological covariances. So in the past it was 50% climatological, 50% ensemble based. Now it's 75-25. And I'll show you at the end we're getting towards 12% of static. So we're trying to get rid of that component. But it's still out there, so that's why I'll still cover that in my presentation. So part one, I got 4 parts here. So only have 33 slides, so feel free to keep up with the questions. So let's cover the methodology and the experimental setup of my experiment. So this is the domain. Our domain for our high-resolution regional system covers most of Canada. We do not cover the small islands in over the Arctic Circle, but we do cover part of Alaska and the northern states of the United States. And for all the experiment I'll be showing today, you have to keep in mind that I'm only using 128 members instead of 256 to reduce computational cost. And all the analysis increments are computed at 10 kilometer resolution. Yep. Oh yeah, and the boundary conditions are supplied by our global deterministic prediction system. But for the ensemble generation methods, we need perturbation in the boundaries, and these are provided by the global eNKF that we run operationally. Everything fine so far? So climatological covariance, I'm pretty sure most of you guys are knowledgeable about the NMC matrix. So this is the method that was developed and used at the National Meteorological Center. So which is now NOAA and CEP. So it's basically we're computing homogeneous and isotropic background error covariances based on differences from forecast of lead time of 24 and 48 hours that are valid at the same time. So there are differences. Like previously, our regional system was on a continental domain, and the fact that that domain was so large, it was not possible to use the Fourier transform because it was so large that we would have some distortion in the grid. So we were forced previously to use spherical harmonics. So spherical harmonics are on the whole sphere. So if you want to increase resolution, you increase resolution on the whole Earth, where you're only using the information over the North American continent. So increasing the resolution was a big problem. So that's why in the actual continental assimilation system, we're still using the background error covariances from the global system. But as we move towards a smaller domain, our national domain, covering Canada and the northern part of the US, we can now use the Fourier representation. So that allows us to reduce the size of the grid, and then we can increase the resolution without busting on the cost. We have to keep in mind that the Fourier representation requires that the domain is periodic, biperiodic. So we have to pad up the domain to have extension on both sides of the domain to avoid spurious increments. So just a way to visualize that is if you have an observation in the Atlantic, you don't want, as the domain is periodic, you don't want your increment to show up in the Pacific. So we periodize the domain and we add some padding area to avoid the spurious increments from going from one side to the other of the domain. So I got three main differences I want to discuss with when we compare the new static B matrix with the global one that is operational. So the first point is in the global background, the static background error covariances, they are homogeneous. So that means that you use the same correlation in the tropics, extratropics, and the polar regions. So in the past, they removed the correlation with humidity in that system because the humidity correlation varies a lot with latitude. So, but going to, as I said, a smaller domain, where like Canada is mostly in the extratropics, so we were able to bring back the correlation with humidity, which I think is a plus for the future because we're going convective scale, so you need the correlation with humidity. Something else, yeah, the variances in the global NMC-B matrix, they have been fine-tuned over the years, and I mean a little bit here, a little bit there to correct for some problems, and it's very hard to keep track of that. So now I'm using the stock variances that gets out of the algorithm. Just an example of that, at some point in the past they had issue with the winds at the surface. So someone just forced a minimum value for the variances of the wind at the surface. But we all know from the physics that the wind at the surface tend to zero. So does the error. The error goes to zero. So when we were assimilating the surface wind and forcing a minimum value for the error variance at the surface, we were generating very large increment at the surface, which triggered a lot of diffusion, and it prevented the information from propagating in time. So now we're using the stock variances from the method. And the third difference is probably the biggest difference is previously in the global system, we were using balance operators. That allows us to differentiate between the northern hemisphere and the southern hemisphere. And so we had to decompose temperature in balanced and unbalanced component, and then we were only linking the balanced temperature with stream function, and vertical velocity was linearly correlated with stream function, and so on. So now we're using the direct correlation, like the statistical correlation between the variables. So we don't use the balance operators themselves. There was a paper by Luc Filion. I think he worked on that like many years ago when he I think he did took some time off at Environment Canada to come work here, and that's what he worked on. So at that time, he showed that they were equivalent in the global system. But I'll show you later, that allows us to have a better balance, like the Ekman spiral is better resolved, and I'll show you that a little bit later. So overall, they're equivalent, but I think there are a little bit of plus value in using that new method to generate the correlations. So that was the first component, the static part of the B matrix. Now let's talk about the flow-dependent part of the B matrix. So when I say B matrix, is the background error covariances, just shortcut.
Yeah,
yes, Ming?
Well, actually, how do you get this MSC method? How long you run your experiment? Which model you are using to get these perturbations?
Well, ideally, you use the exact same model than the one you're going to be using. But when I did compute it, the high-resolution regional system was not operational yet. So what I did is I took the continental system and I interpolated it on our grid. So the error structures are at 10-kilometer resolution, whereas the model itself is at 2.5-kilometer resolution. So we have to keep in mind that in the incremental framework, it's okay to produce analysis increment at a slightly lower resolution than the model is run. It doesn't degrade the result, and I think it is due to the fact that how do you say that in English? I think we have a sub-constraint from the observation. We have less observation than modeled grid points. So at some point, I think we're better off fitting the large scales than trying to fit all the small scales because we don't have enough observation to do that. So I took a month. So that was your question, how long?
1 month.
So a month. So it's it's 120 progs that I was using because we do 4 cycles every day. So it's a sample of 120 members, if I can say so, to generate the perturbation for the NMC method. We have to keep in mind that, like, if we're talking about ensemble Cannon filter, 120 member might not be that big, but we're talking about homogeneous and isotropic structures. So 120 members is more than enough to compute that because it's a diagonal matrix so there's a lot less parameters to fit than the fully flow-dependent background error covariance matrix. Everything is
using 1 year perturbations. So,
but it's 1 year of perturbation, and you have one matrix for the whole year.
I don't know, but they run a lot actually. They collect a lot of perturbations for that. So I don't know if based on your explanations, maybe ends up with lots of results.
Well, there's a variability through the year, so the structure of the correlation varies from month to month. So what we do is we take a month. Yeah. So let's say I take January 2014 to generate my January B matrix, but we have a B matrix for each and every month. So we account for the temporal variability of the structures in the homogeneous and isotropic background error correlations. Yeah, like I do this way, but in the past for the global, they only did summer and winter, and they're interpolated in between to avoid the computational cost of recomputing it. But
okay, that's another. Is there any benefit you make your background error variance change with the season, even season? Did you have any test to show that's the benefits?
I did not do the test, but you can easily imagine that like in North America, summer cases, you got a lot of convective stuff going on, so a lot of fine scales. So the correlation are sharper. If you look at the correlation matrix itself, you see that it's sharper than it is in winter, where, let's say, where I live in Montreal, it's mostly driven by pressure system going up the coast, and they're much larger scales. So the scales vary a lot between summer and winter. So I guess there is some differences, but I haven't tested it. So we're done with the static part. You can still ask questions about it if you want. But let's start with ensemble generation methods. So there is a problem with high resolution ensemble method generation method it's expensive. Like the person running the regional ensemble Kalman filter is the biggest computational resource user at Environment Canada. So we've been looking at different approaches, like practical approach to generate ensembles and approaches that could reduce the cost. And so I'm presenting here quickly a couple of approaches, and we'll go in more details afterward. But so you guys probably all know that we have a global ENKF that runs operationally. So a cost-free approach would be to take their ensemble and just downscale them to our high-resolution grid. So that's basically cost-free. So that will be the benchmark in the forecast comparison I'll show you. Another very cheap approach is an approach that was proposed by Ricardo Tadling at NASA. So, sorry. Basically, this approach is based on the fact that the ensemble, like the way the perturbation evolve, are depending a lot on the ensemble mean itself. So if you have a high quality ensemble mean, you'll probably have a high quality ensemble perturbations. So his idea is to take the deterministic analysis, which is of high quality, quote unquote, and add perturbation to it, so that when you integrate the model, these perturbations will evolve and they will eventually end up being fully flow dependent. The third approach is a little bit more complex than the filter-free approach, but it doesn't cost more. So it's a regional ensemble forecast that is initialized with a simplified version of the square root filter that is centered on the deterministic analysis. And the fourth approach that I tested is the regional ENKF that we have now. That is, it's not operational, it's experimental, but we're planning to bring it to operations within a year. And there is a fifth approach which I have not yet tested, but it's based on an idea from Mark Buhner. So it's a little bit like, I was going to say it's a little bit like the filter-free approach. It's not like the filter-free approach, but the mindset is a bit the same. So by stating that it's very important to have a high-quality deterministic analysis to center the ensemble mean on. So what Mark proposes, you do a full 4D ensemble var for your ensemble mean, so that's your deterministic analysis. And then for your perturbations, you take a simplified approach. So we would do the update to the perturbation using a 3D var with less observations to reduce the cost, because we're using 256 members. So if you do 256 full 4D ensemble var, that is very expensive. But if you do it in 3D var with less observation, then that reduces the cost significantly. So it's just a mindset. It's a little bit like engineering. It's like trying to get most of the results with the lowest resources. But as I said, I have not tested that so far, so we'll not cover that in this presentation. But I just wanted to present the idea to have in mind where we may be going in the future. Yes?
What can you say about the ensemble spread across these different methods? Have you solved that problem?
We'll cover that in a minute. And I have many pictures on the ensemble spread, and we can discuss that when I get those. But keep your question in mind. It's coming in a slide or two. So as I said, the global ENKF downscale on our grid is our benchmark to beat. And then I'm going to be presenting 3 methods: the filter-free, the simplified square root filter, and the regional ENKF. So let's start with the filter-free, a little bit more details on the idea. So basically, what we do is a little bit different from what Ricardo Tudling does, but the mindset is the same. So what we take our NMC B matrix, and we use a randomization of it to generate homogeneous and isotropic perturbation. So these perturbations have the large-scale balance that the NMC has. So we got geostrophy and so on. So we generate perturbation that we add onto our deterministic analysis, and we integrate the model in time. So it's a fairly simple approach. Yes, and the perturbation, as I said, they're centered on the deterministic analysis, but they're fed to it through IAU to avoid creating large perturbation in the model. As I said, the simplified square root filter is a little bit more complicated. So basically, as we are centering the ensemble on our deterministic analysis, we don't care about the update to the ensemble mean, because we throw away the ensemble mean itself. But we are interested in the update to the perturbation themselves. So we take the equation of the square root filter from Whittaker and Hamill, and we simplify it so that we can treat each and every grid point on its own. So we don't need to account for all the correlations and so on. So the 2 simplifications are the following. The first one, we're assimilating fictitious observation at every grid point, so that the observation operator H becomes the identity matrix. The second assumption is we suppose that R, the observation error covariances, have the same correlation structures as the B matrix, so that the Kalman gain becomes diagonal. So if it's diagonal, we can now work grid point by grid point, and we can scale the perturbation at each assimilation step. So basically, the simplified square root filter does exactly the same thing as an ENKF does for the spread. So locally, if you see on that picture, the dotted line represents the 1-to-1 ratio. So if you have a high ensemble spread, the ensemble Cannon filter will squash that spread down because you have a lot of uncertainty, and in that case, observation will have a lot more impact. So you see the asymptote there. So the spread will become lower than the specified observation error. So we do the exact same thing with the simplified square root filter. The big difference with the real square root filter or any ENKF is that we do not touch the correlations themselves. So that means that the correlation gets fully recycled from one cycle to another, and they're allowed to grow over time. So this could be a limitation to the approach, but we have to keep in mind that by doing this, it allows us to treat each and every grid point by its own. So we don't have to run a full assimilation scheme there. We just have to multiply 2 matrices, like you multiply the perturbation by a scaling factor. So it's as cost-free as the filter-free approach, because we don't have to do 256 assimilation steps. So we only have to pay for the model integration of the ensemble members. I'm coming to your question now. So I wanted to show you here in part 2 diagnostic results, so that we have a French expression that in Montreal that say, what does it eat in winter? So probably because the animals don't find a lot of things to eat when there's like 5 feet of snow. So just some diagnostic results just to see what these methods are about and what are their capabilities and limitation. So that's where I'm coming to. this is the mean. These two figures are the mean background error standard deviation for all the methods I presented for zonal wind and temperature. So I don't want to go through all these lines, but what I want to show you is for the high resolution ensemble, so the green line, the red line, and the blue line, the background error standard deviation is in the same ballpark. It's in the same ballpark of the global ENKF as well. We all know that the NMC method tend to overestimate the variances, so that's what we see in this picture. So this is just a figure to show you that the different ensembles have been tuned so that they produce variances of the same order of magnitude. In the same mindset, I produce here the mean horizontal correlation for wind and temperature at around 500 hectopascal. So again, I want you to see that the green, red, and blue curves, which represent the high-resolution ensemble, they're in the same ballpark. However, you can note that for the zonal wind, and we'll see it in the vertical, the regional ENKF has a slightly sharper correlations. The global NMC obviously has the longer correlations, and so does the national NMC. So forgive me, but sometimes I put NMC or RENKF, so regional and national stands for the same thing. So it's a regional domain over the nation, the Canadian nation. It's not often we hear a Quebecer say that. So same thing here. So these are the mean vertical correlation at near 500 hectopascal for zonal wind and temperature. So again, the blue, the red, the green curves are in the ballpark, but the green is sharper, the regional ENKF. And again, the global and national NMCs are the one that has a longer correlation. So these were a couple of figures just to show you that the ensembles are in the same ballpark, and we'll see in the results that there are differences in the quality of the forecast generated when using those ensembles to provide the E and var with a flow-dependent B matrix. So I'm presenting those so that we can just keep in mind that the correlations are similar, the variances are similar, so that we can focus on the differences and try to find out the differences that cause those differences in forecast quality. So coming more specifically about your question, here I present some box plot. So these represent the spatial variability of the ensemble spread on the domain. So you see each and every box have the lower value, the middle value, and the upper value. So these are Q1 and 3, upper and lower value. So quartile, the first quartile and the third quartile, and the median of the ensemble spread over the domain. So these are for zonal wind and temperature around 500 hectopascal. I selected like 500 hectopascal throughout my presentation, but I'm going to focus on the behavior that is similar at all levels and for all variables. So what I want to point out here is if you look at the black curve for the global ENKF, the green curve for the regional ENKF, and the red curve for the simplified square root filter, like the difference between Q1 and Q3 from the beginning of the next assimilation window at hour 3 and at the end of the assimilation window at hour 9, there is no difference in so there's no evolution in the difference between Q1 and Q3. So that shows that the spatial variability does not evolve much in time. Obviously, the mean spread evolves, but not the variability itself. Whereas when we look at the filter-free approach, the blue boxes, we see that the difference between Q1 and Q3 at 3 hours and at hour 9, there is a significant difference. So that shows that the spatial variability is increasing with time. So it's a proxy to thinking like at the beginning of the model integration, we had homogeneous and isotropic perturbation. So these had no spatial variability, and it's now building towards flow dependency. So that allows us to see that the filter-free, even at the end of the next assimilation window, is not yet fully flow dependent. There is still some homogeneous and isotropic structures in there. So I got a 2D figure for the ensemble spread for surface pressure here, just to show the same result but in some other way. So some people sometimes are a little bit more visual. So I got on the left the global ENKF, in the middle the filter-free, and in the right the simplified squirrel filter. And I got the spread, the surface pressure spread maps at 3 hours, 6 hour, and 9 hour. So we see that for the global ENKF and the squirrel filter, already at 3 hour, the flow is already developed. Whereas for the filter-free, we see that it's kind of shady. They're all about the same value, and there's no distinct features in there. So, and we start seeing those features at 6 hour, and at 9 hour, they're more developed. So that shows a strong limitation to this method, because for high resolution data assimilation, we're going towards rapid cycle. So if you take the temporal limit, if we recycle every minute or so, it means that we would be assimilating the observation with homogeneous and isotropic perturbation, which is very similar to a 3D VAR plus sampling issues. So this approach is really not suited for rapid cycle systems. Does that answer your question?
It definitely shows that they all have similar spread, the filter approaches, but if you were to compare that to observed spread, say like if you rank histogram comparing to observations, is there a way to?
I have not done that, but we have packages to do that, so it's a good comment. I should.
Especially with the regional, I've never seen a single model core be able to provide sufficient spread. Even with inflation, you end up having spread collapse as you inflate. You actually have spread collapse, which is the opposite of what you expect.
Yeah.
That's something that I'm battling with a lot of my projects, is establishing good spread so I can get away from the climatological covariance.
Okay, I like that comment. Maybe you should give me your contact at the end of the presentation so that we can discuss that maybe more in depth.
Okay, yeah, we have a lot of overlap in what we're doing.
Okay, thank you. So let's see if this animation is working. It does. So I got it's again the surface pressure spread over the domain for the filter-free, the global ENKF, and the simplified squirrel filter. And here I just for the sake of it, I just want to show the spread during the Hurricane Arthur that hit the East Coast in 2014. So the first thing to see is, I don't know if we see it properly, but yeah, we may not see, but not for the global ENKF, but there is a boundary here, so that the hurricane is halfway across the boundary where we pilot the system. So it's a nice thing to see that even the pilot is perturbed, and there is the right spread for the hurricane through the pilot zone. So it's very important to have a perturbed pilot if you want to generate a limited area ensemble. I've seen some people try to avoid perturbing the pilot and just use a deterministic prediction to pilot the boundaries of the ensemble, but they end up having large bands around their domain where they lack spread. So by trying to avoid having a perturbed pilot, they then need to increase their domain so that they can get rid afterward of all the lateral parts where they lack spread. So I think it's very important to have a pilot that is coherent. So if you want to do ensemble, so you need an ensemble of pilot. So we see that although filter-free may seem to have very strong limitation, in terms of spread generation, it doesn't seem so bad at 6 hours. But then we have to keep in mind now it's at 6 hours, but if we go towards rapid cycles, then it's going to be at 3 hours or at 1 hour where it's going to become a lot more homogeneous and isotropic. And I don't think we see it here, but I have another case here. This is, I think, a week after the hurricane. So we see the tree system. There's a huge depression developing over the northern part of Quebec. But here, I want to point out in this case where we have a low pressure on the east coast with a very strong cold front. So you'll see on the left panels for the filter free and the square root filter, we have high ensemble spread along that cold front. Maybe I have a more explicit picture there. Yes. So here I added the regional ENKF. So sorry, I just moved them around. So upper left is global ENKF, upper right is regional ENKF, lower left it's simplified square root filter, and lower right is the filter free. So we see that on the east coast, if you look at all the three high resolution ensembles, they generate pretty similar structures. Square root filter and filter free are actually almost identical, but you'll see some differences with the regional ENKF, and this is because they do not share the ensemble mean. So the regional ENKF has its own mean, whereas the square root filter and the filter free are centered on the deterministic analysis. So we see that the ensemble mean has a very big impact on the details of the structures themselves. So if your ensemble mean is different than your, let's say, the two ensemble mean are slightly different. There's a phase error between the two. So they both have the same system, but one may be shifted in time or in space and is just 100 kilometer east or west. So that means that your error structures are going to be developed 100 kilometer east or west. So I think it's very important that there is a coherence between the perturbations from the ensemble and the background state that you're going to be using for the assimilation. Because if the perturbations are developed in the wrong area, then you're not going to propagate the information in a coherent way with the background that you have. So this is why I think a lot of people are now working on recentering the ensemble from different ENKF methods to a deterministic analysis, which is used to provide, to generate the background state for the next analysis cycle. Something else I want to point out is the global ENKF also have something going on in that area, but it doesn't have the fine scale to develop the error structure along that cold front. I think I can show you a picture. This is the surface pressure map at this time. So you see it's a huge depression over Quebec, and there's a little bit of an arm going south on the east coast. And if you look at the surface temperature, you'll see there's a very strong cold front in that area. There's another area which I circled in the Northwest Territories of Canada. There's a lake there, and we don't see it much there, but there is a small depression starting to develop. And when we look at the global ENKF, the regional ENKF, and the square root filter, they all get that right. However, the filter free did not get it so much. So there are some cases where filter free does a relatively good job, but there are many misses, especially for cases that would necessitate recycling the perturbations. So far so good. The square root filter seems to have very similar structure as the regional ENKF, which is pretty good because it costs about half the price. But we'll see, they are different. I got a couple of single labs experiment I want to show you. So basically here I've been assimilating one observation of zonal wind at 800 hectopascal, and I'm showing you the surface pressure increments. So that's kind of an image of the background error covariances. I just want to point out that this observation is taken where there is a star there, so it's kind of a continental crest. I chose that specific case to show you today because, as I mentioned, depending on the ensemble mean, like things can get shifted away. So if you're trying to do a single lab experiment in one specific location, let's say we try to do it on that cold front, but if your ensemble mean differ, sometimes you're gonna, like for one system, you're gonna be right on spot, right on the front, and some other system you'll be on the left-hand side or on the right-hand side. So it is to be expected that the correlation structures will be very different depending on wherever you are. So I chose that spot because this continental crest is dominated by the large scale. So a difference, like a small phase error between the different ensemble mean won't affect much the correlation for this case. I did a lot of single love experiment, but what I want to show you here is something that showed up each and every time. So the one thing I want to draw your attention to is if you look at the square root filter, the middle left panel. So I remind you, these are surface pressure increments from the assimilation of a zonal wind at 850. So if you compare the middle left panel, the square root filter, to the middle right panel, this filter free, and to the upper right panel, the regional ENKF, we see that the surface pressure are much stronger. So this is something we see for each and every case. The correlations between variables are stronger in the square root filter. So that kind of makes sense because, as I said earlier, by constructions, we're controlling the variance evolution through the algorithm, but we're not touching the correlation themselves. So they're let alone by themselves to develop, so they can grow larger. Whereas in a fully NKF, they are constrained by the algorithm. So we'll see later that the square root filter does not do as well as the regional NKF, and I think this is why I have the impression that the correlation might be too strong. Like spatially, they're a bit more spreaded, and the cross correlation are stronger as well. So that prevents from fitting as well the observation as the fully NKF, and we don't achieve the same results. So it's funny to see, like, if we go back in time and look at the error, like the spread structure comparing the square root filter and the regional ENKF, they look relatively very similar, but just because of those correlations, the results are not as good. So somebody asked me earlier about the NMCs. These are the two bottom panels, and of course the variances are different, so the increment size is a bit different. But if you look at these two carefully, you'll see there is a difference in the structure. The national NMC is slightly rotated. This is because we resolve the Ekman spiral better. So this comes to show you what I explained to you before. So all the intervariable correlation are fully taken into account through the error statistics. So I got a couple. I don't know what time it is. Am I running out of time? I'm still good. So 7 minutes. Hang on, guys. I got results from full assimilation experiments. You're lucky. I left out 2 experiments, so I just have a couple of slides here. So beware, these figures are very busy. So the difference in colors in these figures are for different experiments. So in that case, the cyan color is for the 3D VAR using the global NMCB matrix, and the magenta is using the national, so the high resolution B matrix. So these are error standard deviation when comparing forecast against radiosondes. So I got on the upper left the wind speed, on the upper right the geopotential height, lower left temperature, and lower right the dew point depression for humidity. So you'll see I have superimposed the curves with circles. So whenever there is a circle, the color dictates who's the best. So if it's magenta, it means that the national NMC is better, and if the circle is full, it means that it's statistically significant above 90%. So there is a second legend. In the upper left in the lower left panel, so I superimpose the analysis fit to the observation, the 12-hour forecast, 24-hour forecast, and 36-hour forecast in the same figures to avoid having 12 pages of figures to show you guys. So basically, I think the colors speak for themselves. So we see that for the analysis fit to the observation, the national NMC, the high-resolution NMC B matrix, beats the global B matrix. And we see that for the forecast, it's mostly magenta. So that, again, the high-resolution NMC is slightly better than the global NMC. I think they're not statistically significant yet because I only have a month of forecast. And these are against radiosondes, which are every 12 hours, so it's kind of 2 runs per day for a month. So maybe if I extended the period, we would get something a little bit more significant. So I think that the fit to the observation is easily explained by the structure correlation themselves. They're at higher resolution. The correlation are sharper, so that allows us to fit the observation better. And in the end, it translates in slightly better forecast. As I said, I'm not presenting the results for all the methods. I withdraw the filter free because it degrades the analysis fit to the observation, and it also degrades the forecast when compared to the global ENKF. As I said, the covariances are still developing through the assimilation window, so it's kind of halfway between flow dependent and a static B matrix. So as I showed in my first slide, the flow dependent matrices often outbeat the 3D VARs. As for the square root filter, I mentioned earlier that we do not fit the observation as well as the NKF. I think this is due to the fact that we let the correlation structure grow, and whereas the NKF controls them every cycle. But we do not fit the observation as well, but the 0 to 48 hour forecasts are comparable. There is no statistically significant difference between the forecast score. So that's why I'm not showing them, because the lines are superimposed and it would be a bit lame. But now I'm showing you. So the figure is the same as previously, except the color change. So in black, it's the EN-VAR using the ensemble from the global ENKF to provide the background error covariances. And in green, it's again the EN-VAR, but using the ensembles from the regional ENKF. So similar to the 3D VAR comparison I just showed you, the higher resolution ensemble allows for a better fit to the observation. And it's mostly green everywhere, so that shows us that the use of the regional NKF to provide the EN-VAR with flow-dependent background error covariance is beneficial, slightly beneficial. Overall, we're talking about 2% improvement if you average everything out at the surface and the upper air. So the main goal was to develop something that is at least as good as the global ENKF, which we achieve, plus we improve it by about 2%. So it's fairly good, I would say. Here I'm comparing the hybrid version. So here it's an hybrid. So in black, it's the global hybrid. So it's a hybrid using the global ENKF with the global NMC matrix. And in green, it's a hybrid using the regional ENKF with the high resolution NMC matrix. And again, the conclusion is the same. Higher resolution structure, sharper correlation allows us to fit the observation better, and we have a better forecast score. So we can see here that we significantly increase the scale in wind speed near the jet, all the way up to 36 hours. For geopotential height, we got some improvement in the troposphere. Whereas for humidity, we have some improvement at 12 hours, but it's not significant beyond that.
So what's the weighting between
I'm coming there. Next slide. So that was the best weighting we have so far. So I did some tests. We can see them here. I started with the operational 50-50% for static and dynamic B matrix, and I went towards 100%. So we got 75-25, 87.5, 12.5%, and 100% flow-dependent dynamic B matrix. So we see that so 0%, I'm showing the overall improvement against what is operational against 50-50%. So we see that for surface scores, the more we are flow dependent, the better it is. However, for the upper air, we see that 100% flow dependent B matrix is not the best. We kind of benefit from adding a little bit of the NMC matrix. And again, I think this is because we have to localize ensemble members because of the sampling issues. Because in the long distance, the correlations become small, and it's very hard to sample small values where the sampling errors is high. So we have to localize them and put them to zero at some distance. Whereas we don't have the sampling issue with the static component with the NMC method. So I think using a little bit of the static background error covariances allow us to get some correlation in the long scales, and these are basically based on the large scale balance, so like geostrophy and so on.
Are these improvements in forecast or in fit to ops?
Forecast. Forecast 0 to 48 hours. So they're all blended together just to bring up a number at the end. But I got detailed figures if you guys are interested. We can go to my office after and look at them. So I did the kind of same experiment, but playing with localization. So I think the Canadian systems are known to have very high localization length scales if you compare to what they use in the RAP system, or even the French at Météo France. Like I think at Météo France in their high resolution system, they use like something like 500 kilometer. Or what do you use, Ming, in the RAP? 110. So we use very large localization length scale. So I actually fiddle out with the parameters. This is very fine-tuning, I would say. So we saw that there is an improvement in localizing more the ensemble. Here I show you the results for the regional NCAR, but I have to say that all ensembles benefited from increasing the localization, so reducing the length scale at which we localize, at which we bring the ensemble covariance to zero. I had a comment from our meeting at NOAA that maybe I should try something more aggressive than 1,400 kilometer and one length scale in the vertical. I will do that just to see when we saturate. That would be a good experiment to do. So I went through my time, sorry guys, but conclusions, I got only 2 slides. So basically for climatological variances, we're now using the Fourier representation that allows us to increase significantly the resolution. So now we're fully using all the multivariate correlation, so that gives us better balance, and we're now allowing humidity correlation, which is good in a convective scale system. The variances are native and they're not being tuned as they were before. So I think that what we saw today, we saw that the filter free is not suited for rapid cycle, and there is a need to recycle perturbation to be able to get the right spread in some like slower developing areas. The square root filter is a cheap solution. Maybe I should try to work a little bit on the algorithm to benefit from updating correlations to see if we can do as well as the regional ENKF, because that would be great, because it would be half the cost. The global ENKF is a good baseline. It's hard to beat. And in all cases, it's necessary to pilot the regional ensembles. So far, so good. The RENKF is working well. I think it could benefit from recentering. We're actually working on that. I got a couple of next steps. So recentering is important. We want to do scale-dependent localization, reducing the cycle time. And of course, I've been testing it with 10-kilometer model. We're now going to plug it with the 2.5 model. And I want to test using it with less members, because if I come back here, at first I was using 256 members, which is cost prohibitive. And I realized there is no statistically significant difference in the forecast scales when going down to 128 members. I think this is due to the fact that we're running the system on a well-observed domain, and like Peter Tokamer in his system, it's global ENKF with 256 members. He's shown that it was useful in this system to use a lot of members, but I think the improvement he saw may be more in less well-observed area. So I'll probably play around and see if we can reduce the number of members to reduce on the cost without reducing the quality of the forecast. So as I said earlier, my work as a PhD student, my work here on high resolution of surface wind data, and also what I'm supposed to do as a postdoc to assimilate radiance observation at high resolution, we could not work on that fully without having a fully flow-dependent background error covariance at high resolution. So I think so far so good, it's mission accomplished. We can now start to work on the thing we're supposed to. I'm supposed to work on radiant stuff, so I can get back to it. I'll still keep on fiddling with the RENKF group, but I'll go back on the observation side, I think, for the next year. That's about it, guys. Thanks for your attention. We rented the room at a very low cost, up to 3 o'clock. So if some of you want to stay and discuss more, the room is ours. Thank you. Any more questions? Yes. Well, so the question, I'm going to repeat the question for the recording. So I've been asked how it relates to convective scale modeling and assimilation. As I said earlier, in our variational scheme, we're based on the incremental approach. So in that case, we can do the assimilation at the lower resolution than the model is. So we do not have enough observation to constrain all the degree of freedom in the model. So I think it would be kind of useless to try to fit everything, because it would be suboptimal. So the incremental approach tends to fit to constrain the large scales, and it is up to the model to develop the finer scales. I guess that's how I see it. So in these experiments, I was using a 10-kilometer model because I did a lot of experiment, and the 2.5-kilometer model is being transferred to operation. So there's a couple of months wait there. So I guess the improvement we saw there, we'll see then when we're going to be using the 2.5-kilometer model. But I don't know if it's going to be better. That's up to the model to see how it reacts to the large-scale information we're bringing.
Do you account for the model error specifically?
What do you mean? In the B matrix or?
In the forecast, basically, so that it can go to the B matrix.
Yeah, so I'm going to refer to Peter Tokamer's paper. The way he accounts for model error, I think, is by additive inflation to the ensemble analyses. So that's how it's accounted for. I know other systems have other ways, like how do you call them? The prior relaxation to prior, or multiplicative inflation. So in this system, we do additive inflation. Yes, Anna.
Do you also do, I think in the global system at least at some point they did different physical parameterizations for different members. Do they do it in the regional?
We dumped that out for the regional ENKF. So just for the sake of the recording, in the global system, there are still multi-physics packages. So each member has its own physics library. I think there are two limitations to that. It's costly to maintain because you have to maintain older physics packages. And the other thing is Jean-François Caron, one of our team member, he spent some time at Météo France and doing diagnostics on the ensemble with Benjamin Ménitrier. And they figured out there was some weird stuff going on near the surface. And I contributed a little bit to that discussion and brought the idea that for some members, they had different description of the surface roughness, and they had kind of four different types of ensemble members that had different packages near the surface. And these can cause biases, which translate in very long correlation length scales. So I suggested that when you're computing the ensemble mean, you want the perturbation, so you're removing the mean. So we were computing ensemble mean for 4 subset of ensemble, and then we got rid of those long correlations. So I think in some case it can cause some problems like that. In that case, it was generating biases in the perturbation. So there are limitations. So for the regional ENKF, we got rid of that component. And we also reduced the amount of additive inflation we are using. They were fine-tuning it, and they ended up reducing it a little bit.
Great. Any more questions? Anyone want this?
Nobody wants a microphone. I'm stuck with it.
Yeah. Okay, I think actually anyone free to go and all stay here, talk with Joe. And his office up to FL3, first floor.
1034.
1034.
Yes, FL3
Okay.
10 to 34. I'm there this afternoon. Tomorrow I'll be at CSU. So
you are going to stay here for a couple of hours, right?
Yes.
So this afternoon. So feel free to drop by, talk with Joe.
we still have the room for 45 minutes, so we can stick around as well.
Yeah.
Thank you.